I'm Tanusree Parbat from IIT Kharagpur. I'm here for presenting my paper, Encrypted SQL Arithmetic Functions Processing for Secure Cloud Database. These are the outlines of my presentation. This is the introduction part related to my work as developing smart technology and global information and communication infrastructure are responsible to generate huge amount of data day by day. And to store and process those huge amount of data, cloud computing is the ultimate platform. So, but security is a big issue. Cloud server provides basic security according to their agreement, but we get to know from various sources that storage data misuse, outsourced data disclosing. So these are incurring a significant risk for the cloud applications. Now, data owner no longer satisfied with that basic cloud security for processing or preserving their data inside the cloud. So there are two possible solutions to solve that problem. First one, whenever data is generated, then segregate those data into sensitive and insensitive data and upload the insensitive data to the cloud and keep the sensitive data in the local storage. This solution can solve the problem of security, data security, but this incurs huge processing overhead at the client side. And the next solution is, before outsource the data, encrypt those data and upload it to the cloud. This solution can solve the problem of data storage security, but what next if data processing is required on that outsourced encrypted data? Now, data owner either provide their secret key to the cloud, or they retrieve their database from cloud side to their side and decrypt it, process it, and then again encrypt and upload to the cloud. So if we do so, then the aim of cloud computing is defeated. So we required a secure direct processing over the encrypted data. Now for this is the main objective of our work. So for this, homomorphic encryption technique is the preferred choice to process the encrypted sensitive data without any intermediate decryption. Now, using that encryption technique, if we encrypt a message bit M with the secret key P and a random number Q with a small noise R, it generates a noisy ciphertext. Here 2R, this 2R is added. This is the noise, this added with that term. So if we perform addition between two noisy ciphertexts, then this noise is also added. Here it is 2 into R1 plus R2. And if we multiply this ciphertext, noisy ciphertext, then noise growth is also increased, and it's almost square. So for our circuit-based representation, we realize that if we do repetitive homomorphic addition or multiplication, then this noise is increased too much to get back the plain text, original plain text. So in 2009, Jeune worked on that noise and proposed bootstrapping technique with homomorphic encryption, where after homomorphic operation, homomorphically decrypt the cipher and deciphering it by encrypted secret key to reduce the noise. So using this technique, any arbitrary operation can be possible. So this encryption technique is fully homomorphic encryption techniques, and we use this encryption technique. Using that encryption technique, we are going to realize how SQL processing possible over the encrypted data in the homomorphic domain. Now there is some literature. They already there is some encrypted database. They are all they support only limited numbers of queries and limited mathematical operation. Here is 0DB, one of the encrypted database. 0DB, all encryption operation occurs on the client side, and EncryptDB support only limited number of queries, and complex mathematical functions are not addressed there. In SteelDB, decryption is required for the computation, and always encrypted with secure enclave requires a key to enable the enclave for the computation. Another author proposed few FHE-based secure cloud analytics solution, but they have used only addition and squaring operators. Now, Kaiping et al. Proposed an efficient multi-party computation cloud framework under only partial homomorphic encryption. Another paper presented homomorphic arithmetic operation like addition, subtraction, multiplication, and division under the HELIP library. Though the basic encrypted SQL queries processing techniques with FH are already discussed in previous literature, but encrypted transaction-related SQL queries with complex mathematical functions are not handled. So for FHE consideration, when we translate these mathematical functions algorithm in a circuit-based representation, then underlying processor cannot be processed those operator in a straightforward way. So that is the challenge to implement this mathematical functions in a FHE domain. So here in this paper, we implement some complex mathematical functions which process on the encrypted data. And these mathematical functions are absolute, ceiling, floor, sine, square, power, square root, which are heavily used in cloud database query. Sorry. So here, in order to implement those mathematical functions, most of those mathematical functions receives floating point numbers as input. But existing FHE scheme do not support processing of floating point numbers in encrypted domain. So to handle this problem, we proposed a floating point number representation. There's application specific floating point number representation. There we consider floating point number with 2 decimal place, and first we normalize the after decimal part, and then we encrypt those normalized part, like first digit after decimal and second digit after decimal separately along with the integer part. Now here in this diagram, there 2 to the power 3 bits are preserved for the after decimal part, and remaining n minus 2 to the power 3 3 bits are preserved for the integer part. Now, if we want any integer related operation, then n minus 2 to the power 3 bits will be processed. Otherwise, n bit will be processed. Now, here I'm going to discuss our implementation details. Implementation details of some complex operator with SQL queries. So this is the basic mathematical functions we have designed in the homomorphic domain. First one is ceiling functions. In case of ceiling value, we first check the decimal part, encrypted decimal part with the encrypt threshold, that is 0, using our FHE is equal module. If that module generates 1, that means decimal part is equivalent to encrypted threshold, I mean encrypted 0, and then encrypted integer part itself is the ceiling value. Otherwise, integer part incremented by 1 using FHE addition module. In case of floor value, it always take encrypted integer part as floor value. In case of sign function, then MS bit, if the MS bit of the argument passing through these sign functions, if it 1, then that sign functions returns negative, otherwise it returns positive. This is the this implementation This is implementation of absolute value and multiplication operation. If we calculate in order to calculate the absolute value, first we send most significant bit of the encrypted numeric expression as a select input to a decision making module, that is encrypted multiplexer, and first input of that multiplexer is encrypted numeric expression, and second input is 2's complement of that numeric expression. If that MS bit is 1, then 2's complement of that numeric expression will be the ceiling value, will be the absolute value. Otherwise, first input numeric expression will be the absolute value. So here, this is encrypted, this diagram for encrypted multiplication operation. So here we have use shift and add method, where one bit of multiplier is multiplied with every bit of multiplicand. Here in this diagram, you can see ciphertext 2 is here multiplier, and ciphertext 1 is the multiplicand, and encrypted theta, that is initialized to 0. Now, this encrypted multiplexer will, whatever result generate from this encrypted multiplexer, that result will be shifted right before one bit right before adding with the result val in order to get the partial sum. In this way, we are implementing the multiplication operation. So in using that multiplication operation, we implement the squared function also. Now this is the implementation of power function. In order to find out a power value, we require two arguments. One is base, another is exponent. So in that homomorphic encryption domain, if we encrypt only base value, and we unencrypted the exponent value, then we execute a for loop up to exponent, and then perform multiplication operation between perform power and encrypted base, where power is initially 1, encrypted 1. Now this is a straightforward way to compute the power function. But what happened when exponent is also encrypted along with the base, encrypted base? So in that case, this condition I less than encrypted exponent, this condition will cannot be processed by existing underlying processor, because where loop iteration will be stopped, it is not decided. So our observation, not only from the engineering aspect but also for application aspect, this operator can be feasible in homomorphic domain, can be feasible in encrypted domain, if and only if we consider some ranges. Here we consider maximum loop count AN, and range encrypted 0 to encrypted n minus 1. Whenever the range value less than the encrypted exponent, then multiplication result will be reflected as a power the
So is it okay? So Tanusree, I guess that you are muted now.
Hello.
Yes, I guess you dropped off.
There is some network issue, I guess. Sorry.
No worries. So we couldn't hear for the last 20 seconds around. So if you can please
okay,
repeat that.
Sir, So this is the numeric expression. This numeric expression belongs to a certain range. Here is the lower range, and there is some sub ranges, intermediate sub ranges. Here encrypted 1, 4, 4, 9, 9, 16. So this column, square root column, this column is hold the square root value of lower range, and their range offset is hold for every sub range, and it holds the average difference between every non-square value within a specific range, upper range and lower range. So here FHE is greater module, and if multiplexer 1 is used to find out the range offset, and FHE is lesser, and max 2 multiplexer 2 is used to find it near lower range, and square root this FHE is lesser, and multiplexer 3 is used to find out the nearest square root value. After finding nearest offset, range offset, nearest lower range, and nearest square root value, we find out the difference between numeric expression and lower range, and after that we perform the multiplication using the range offset and the difference, and whatever result is generated, that multiplicative result is added with nearest square root value in order to get the square root result. So this is the working module. Here we have used Prima Indian diabetes data set, and we are user transmit a query with power value and a group by operator. So after receiving that query, cloud perform where condition based on that encrypted data, and whatever the resultant data will get, based on top of that, power function will be executed, and after that whatever result is generated based on that, powered by operator operate and create a similar group, and then transmit that encrypted group to the user for final decryption. So this is the I've shown this is the only one example. Similar way we can handle any query which SQL query which is supported by TPC standard. Now this is the implementation part. This is experimental result. We have to implement we have to implement our proposed module under TFHE library and GPU based NFHE library in Google Colab platform. This is the experiment result. Now this is the bitwise performance of the square root function, absolute function, square function, and ceiling function. This is the power function, bitwise performance of power function. Now, in conclusion, here we focus on designing encrypted SQL query execution with complex mathematical functions. In our future work, as per application requirement, we will consider to explore other mathematical functions. Parallel implementation technique also will be explored to improve the performance further. These are the references I have already mentioned in my paper. That's all. Thank you for your patience and time.
Thank you. So, questions. I can actually start with a question. So this is more of a clarifying question. So what I was wondering is that you talked about this encrypted SQL queries and made a convincing argument that we really need this kind of SQL engine which can work on encrypted data. However, the mathematical functions that you implemented and have shown, is it specific to SQL or like in the implementation of the design front, or is it generic? Like, you know, I have given you some encrypted data and you want to do some complex mathematical operations on them. So is there anything specific to SQL, like sequential query language or relational calculus in your scheme?
It is for generic purpose. Actually, sometime we require for transactional related, sometimes we need transactional related queries. So there we can use this mathematical operation.
But this is not, your methods are generalizable to even non-SQL use cases, right?
Non-SQL.
Like where you just have some encrypted data and you want to do some mathematical calculations on it for various reasons.
Yes, sir.
Okay, sounds good. Any So any questions? So any other questions from the audience? If not, let's thank the speaker. Thanks a lot, Tanusree, for this
Thank you,
fantastic
sir.
work. And let's move to the next talk by Nandish. So Nandish, if you're there, can you please set up? And his research strives to create countermeasures so as to make machine learning models more reliable and suitable for practical deployment. So without further ado, Nandish, please take it away.
Thank you, Prof, so much for the lovely introduction. So hello, everyone. Good morning, good afternoon, or good evening, depending upon whichever part of the world you're joining in from. Tonight, I will talk about our paper, Robustness Against Adversarial Attacks using Dimensionality. So let's get started. So just to give you a quick outline of the slides that I have. So I will start by quickly mentioning what adversarial samples are in the first place and why they're relevant. Then I'll touch upon the issue of high dimensionality and its corresponding problems and issues that come up with it. And then keeping all of these in mind, I will specify our contributions and the design considerations that we had to create a framework for robustness against adversarial attacks. And thereafter, I will, of course, present the experimental results and mention some key findings and so on. And finally, I'll wrap up with some thoughts on the future works that we want to do in this direction. All right. So adversarial attacks were first observed as anomalies in the image classification systems around about the year 2014 for a specific classifier, which is a model trained on a data set and a particular correctly classified sample. The corresponding adversarial sample that one can generate using some adversarial attack method would be a sample which includes certain structured adversarial perturbations within it, which would be invisible to the human vision, but picked up by any machine learning model which is trained to do that specific task. This therefore creates a discrepancy at the inference decision, right? So in the diagram that you see on the right, F1 is my machine learning classifier, which in most likelihood will be a neural network in this case, and F2 is a human annotator, right? Now, when I pass a sample through either of those, they will give me a predicted output. And if there is a discrepancy at the predictions between F1 and F2, then we have the emergence of an adversarial attack. So to define it in a more specific and concrete way, mathematically that is, if we have like a space of samples from X, if we pick up two samples X and X star, and we have a norm D that is defined in the space X2, and we have a predefined threshold, which is the limit on how much perturbations we're allowed to make to the sample to create the adversarial example, which is delta, then the equation that I have presented on the left of the slide must be satisfied, which is that for the machine learning classifier, which is F1, F1 of X is not equal to F1 of X star. So there's a discrepancy there's a change in the predicted output of the machine learning classifier between samples X and X star, but no such change is detected by the human annotator. And the amount of perturbation that we have introduced to create this specific adversarial sample is limited by delta, because if you keep on changing the image to an extent where it becomes visible to the human annotator itself, then you have changed it enough to sort of label it as a fresh image. It's not an adversarial sample anymore, right? So that's basically the idea of adversarial examples, and they are a key deterrent to most machine learning applications that we have, because these are very easy to create, number one, and number two, if you create an adversarial sample for a specific classifier, it also transcends to other classifiers, right? That transferability property is also a key deterrent. And the other thing is that if I, like, it's a very obvious practical example, which is that if I take an adversarial sample and if I print it out and paste it somewhere and take a picture of it, it still remains an adversarial sample, which has a very practical use case in messing up autonomous driving, for example. So if you have a stop sign, I can, like a stop sign on the roadside, and I inject certain specific structural noises to that stop sign, and I create a fresh version of it, and I print it on and paste it where the actual sign was, then the human driver will of course still consider it to be a stop sign. But if you are on autopilot for some vehicle, then the dash cam of the car might consider it to be an adversarial sample, and that might lead to a crash which can have catastrophic impacts, right? So I mean, it can, the applications or the mal applications of adversarial samples can range from minor misclassifications to something as serious as the one that I mentioned just now, right? So this is a serious problem that we are dealing with. Now, so the idea here was that we wanted to sort of understand why adversarial examples are easy to generate in the first place. So our end goal is to prevent the creation of adversarial examples, and we do that by understanding the geometry of high dimensional spaces of the trained manifolds of the classes where these samples exist. So we therefore pay particular attention to the behavior of the data points in the high dimensional setting, and we look at their distribution within those manifolds. Now, what is interesting here is that we note that there are certain properties of the objects in the high dimensional setting which are peculiar, like the fact that when you have an object existing in a very high dimensional space, then most of its volume lies near the surface. There is a mathematical proof for it, which part of it we have presented in the paper as well. But the idea is that when we have such interesting and counterintuitive properties of high dimensional spaces that we can establish mathematically, and we see a relation of that to a practical example in adversarial samples that we have at hand, we are trying to relate the two and use ideas of dimension reduction to address the problem, right? Now, this is like the idea of relating adversarial examples to dimensionality is a popular idea. It has been It has been well researched, and we from our group also have contributed to that research a few years back. But now what we are trying to do is we are trying to build on it, and we are trying to therefore design countermeasures to adversarial attacks using dimensionality. That's the broader idea of our work. Therefore, just a quick look at the contributions that we've tried to make in this paper. So first of all, we design a parallel pathway of simultaneously carrying out the classification task and the detection of adversarial perturbations in the samples. We do these in parallel to increase efficiency. Number two is that we use dimensionality reduction to eliminate adversarial perturbation from only those samples that are detected to be adversarial in nature. And this is important in terms of efficiency, and I will focus on that in the next slides. And then, of course, we've tested the proposed framework for all the necessary benchmark, right? So in order to do all of this, we had to consider some specific design ideas. First of all, it's a fact that dimensionality reduction is not targeted and therefore may reduce useful information from the samples along with adversarial noise. So while dimension reduction is useful. Sorry. Okay, I'll continue. So
yeah.
So while dimensionality reduction is useful for eliminating adversarial noise, this process may also make the original machine learning task difficult for a trained model, right? Because essentially you are losing out on information. So therefore, how much variability to preserve in the samples is a critical design decision, and that we had to tune for over multiple iterations. Also, its dimension reduction is an unnecessary overhead for samples which are clean, right? And it may slow down the overall system, and this scales significantly when you have a lot of samples to deal with, right? So we kind of try to address this situation in an intelligent way by selecting which samples to expose to dimension reduction and which samples to let just be as they are before sending them as inputs to the machine learning model, which is our classifier. So our task is still image classification. Now, adversarial examples crafted by adversaries are fewer in number, and naturally they are lesser than the naturally occurring clean samples, right? So the system that we generate is likely to encounter many more clean samples than adversarial samples, and the clean samples will not require dimensionality reduction. So that's something that was a key factor in the design choices that we had to make. Now, we have designed the framework in a way that the dimension reduction loop is activated only for those adversarial samples which are fewer in number, and for the most of clean samples that are fed into the system, they are directly sent to the classifier and then onto the output. By checking for the presence of adversarial perturbations and only then reducing dimension, we're ensuring that the model performance for the clean samples is not hampered, right? So those were a few quirks to understanding how we developed the pipeline, which I am about to present now, right? So this is the overall schematic of what is going on, right? So this pipeline is set up using parallel pathways for the primary machine learning task of classification, which is done by the main model, and the additional task of detecting adversarial samples using the adversarial detector. Now, at the input side, the input samples are sent in parallel to both of these networks, the main model and the adversarial detector. Now, of course, we have tested this entire setup for multiple neural architectures and so on and so forth. And I'll describe all of that in the result section. But what we have essentially from the design point of view is this, that the main model generates the probability distribution over the classes as expected. And the adversarial detector is essentially a binary classifier that labels the samples into either clean samples or adversarial samples. So if a sample is found to be clean, then the corresponding channel is enabled so as to map the output of the main model onto the final output of the system. And if the sample is found to be adversarial, then the other channel is enabled, which feeds the input sample to the dimension reduction block. And then it again goes through the loop and goes back to the input side and is again fed to the parallel pathway of the main model and the adversarial detector. In the next loop, if it is still an adversarial sample, then again another round of dimension reduction happens. And in the next pass, if it is not an adversarial sample, then the output of the main model is mapped to the final output, right? So moving on to the experimental setups and the results. Now, I know there's a lot of information in this page. So what I would like to draw your attention to is this, that all the 4 tables are essentially the repetition of the same experiment for different neural architectures and adversarial attack modes. So like following only one of those would be enough to have an idea of what we are essentially trying to study. So to start with, we study each component of the infrastructure separately first, and then we look into the performance of the overall framework under very specific circumstances. So to start with, we note the accuracy of the main model, which is the primary classifier, when it is exposed to clean samples. And this is our baseline, right? This is the highest possible performance that we may have given the specific set of neural architecture and the data set, the corresponding data set, right? Next, we look at the drop in performance of the main model when they're exposed to the adversarial samples. Now, for all of these tables, we have used a specific, as I mentioned, combination of a neural architecture and a adversarial attack. And for each of the studies, we have looked into 3 different data sets. That's MNIST, CIFAR 10, and CIFAR 100. Okay, so the first 2 experimental setups I just talked about. The next one is regarding the adversarial sample detector. And this is very important because high accuracy of this component is extremely critical to the overall performance of the pipeline, right? The error in the adversarial detection will kind of be propagated to the overall output error of the system as we apply the adversarial perturbation reduction loop only to those samples that are identified to be adversarial by this particular detector, right? Now, the intuition as to why this adversarial sample detector works pretty well in this particular case is that a neural architecture that is vulnerable to picking up adversarial noise and therefore misclassify and fall prey to the attack will also be sensitive to that exact same noise when that particular neural architecture is being trained as an adversarial detector instead of being a regular classifier. So if the architecture is sensitive to the noise for the attacker's perspective, it is also sensitive to the noise on the perspective of somebody who has trained the adversarial detector with clean samples and adversarial samples, right? So that's the idea there. Now, having detected which samples are clean and which samples are not, we study the impact of using dimensionality reduction techniques and how that impacts the performance of the actual classifier. And we have looked into two most popular and commonly used dimension reduction techniques. That's singular value decomposition and t-SNE, that's t-distributed stochastic neighbor embedding. Very standard and popularly available. So what is important to note, as I keep mentioning again and again, is that the adversarial samples detected by the adversarial detector are exposed to dimension reduction only, right? Okay. Now, once we are done with dimension reduction, finally we check the performance of the overall framework. We use two different setups here. One is a more practical version where we have 80% clean samples and 20% adversarial samples. This is more likely to happen in the real world. But we also considered a rather worse case scenario where we have 50% clean samples and 50% adversarial samples, just in case, just to check the performance. Now, yeah, to explain everything from all of those numbers is a little difficult. So I think it makes more sense to look at some pictorial representation for a better understanding of the results that we have. First of all, right off the block, the observations are quite consistent across different choices of neural architectures and adversarial attacks. So again, like the four sets that I have presented here are for 4 different combinations of neural architectures and attacks, but following one of the 4 would be sufficient because as you can see, it's quite consistent all through, right? Right. So what have we observed from the experiments that we have done? So we of course see that the adversarial samples are able to bring down the accuracy of the main model significantly, from 15 to 50% in some cases. But the introduction of dimensionality reduction successfully prevents that. Dimension reduction works very well for eliminating adversarial perturbations and proves to be a good technique for correctly classifying the adversarial samples after going through the loop. And we have seen a 2 to 5% performance within the range of accuracy of the classifier without any adversarial samples. That's the baseline that I talked about in the beginning. And as we had expected, as the intuition suggested, the adversarial detector, which is a model specifically trained to detect adversarial samples, is extremely efficient. And we have a fair good amount of understanding as to why that might happen. And we see that it is always accurate in excess of 98% for all combinations of models and attacks and data sets. And this is very critical for the successful working of the parallel nature of the pipeline that I just mentioned. Now, since dimension reduction reduces, or it actually can reduce some important information from the clean samples, the parallel pipeline is necessary to increase the overall accuracy of the framework when the input samples are a mix of clean and adversarial samples, right? But one observation that we have had is that there is not much of a difference between using either of SVD or t-SNE. Whichever way you reduce the dimension, we have quite comparable results. And the overall framework is, in both cases, quite robust against adversarial attacks, whilst also being functionality preserving. Now, of course, since we have considered 2 different scenarios, one more practical version and one kind of the worst case scenario, the framework consistently generates good performance of accuracies within the range of 1 to 2% of baseline for the practical scenario and about 2 to 4% of baseline for the worst case scenario, which is 50-50 clean and adversarial samples distribution, which is unlikely to happen, but we just wanted to check. And then we also did a little bit of a system performance check, where we wanted to study how much time is consumed in the inference process for the setups, because that's another key aspect to look at. This gives us a good understanding of the efficiency of the infrastructure. The inference time per sample, as you can see, is quite comparable for the main model and the overall pipeline. The main model is without the adversarial detector and the loop and anything of that sort. That's just the simple classifier, which is vulnerable to adversarial attacks. The overall pipeline is quite robust against the attacks. Yeah, so the results here are also carried out for that set of two different scenarios, one more practical, one being the worst case scenario. And the results indicate that the framework is able to deliver robustness without too much compromise on the corresponding overheads that we might have. Yeah, and going ahead, we are looking to extend this idea to video streams instead of images, and we want to study the real-time applicability of the framework in greater detail, so as to find more practical use cases so that this can be deployed in public. I mean, that's the holy grail, right? When something of this sort can be incorporated within the dash cam of a car, I think that's the moment when we will have truly succeeded in what we started off doing in the first place. Yeah, that's kind of it from my side for this presentation. Thank you all for listening in, and I will be more than happy to answer your questions.
Right, so questions? So Nandish, in the meantime, I guess the questions will, and please write the questions in the Zoom chat, or you can raise your hand or even unmute yourself. But while those things are coming, so Nandish, what I was wondering is that what is your threat model here? Because, just to actually, this is more of a clarification question again, but I was just wondering, because if you're talking about a more omnipotent adversarial attack, who knows in and out the systems and who have control over how the machine learning model will work, your method might or might not work. However, are you thinking of a black box assumption, a white box with some limited access assumption? Like, what is?
Okay. Right. Okay. So the threat model is any adversarial attack that has access to the main model, which is the classifier, right?
Yeah. Mm-hmm.
So the adversarial attacker may, so the adversarial attacker may have access to the neural architecture and the weights and everything that pertains to the classifier itself, right? But we are assuming that the adversarial attacker does not have access to the entire pipeline. Okay, right? Because typically what happens is that when you have attacks against any models, which can be both white box or black box, they have access to the specific classifier that we are considering, right? But in fact, if the attacker is given access to the neural architecture and the person knows about how this entire thing is happening, then there is not much of a problem, except somebody might try to create adversarial samples for the adversarial detector that we have in place, right?
Exactly. So that was my, I mean, that's what I was thinking. Like, is it an arms race? Like, what is the power of the adversary?
Right. Exactly. Yeah. So in that case, we have to, so for that we need to define, like, so this is kind of more detailed it's presented in a more detailed way in the paper, where we mention specifically that the adversary has access to the classifier itself, but does not have access to our entire pipeline. But in the future, if that case does arise, then what we can do is we can sort of cascade this pipeline into another one, so that every time we add a new layer, we are adding one new layer of adversarial defense, right? But then that sort of arms race will always go on.
Okay. That's good. So in the meantime, I guess Ileana has a question on Zoom.
Yeah.
I'm just going to read it. I imagine that the best dimensionality reduction depends on the geometry of the space. Could you share any lessons learned about how to make good choices?
Right, a very interesting question. So what we were expecting is that, which is why we use two different ways of dimensionality reduction. And within that also the threshold as to how much information to preserve and how much to throw away and so on and so forth. All of these considerations when we were checking with the experimental results, we were expecting to see a lot of differences, but then those differences did not come up in our results. So which is not necessarily a bad thing, because it means that our method does not necessarily depend on any of those dimension reduction methods. You're free to use any. You can use a linear one, which is SVD, or a non-linear one, which is Tisney. But yeah, we also had some similar apprehensions, which is exactly why we chose to study the setup with different dimension reduction techniques, but we did not see any results, any differences in results for the specific choice.
Sounds good. Any other question? Okay, if not, thanks, Nandish. Fantastic work. And as you mentioned that, I guess this is started with the whole adversarial example that can stop self-driving cars. So we are really looking forward to the next genesis of this work, where you can actually make the car work again.
Right.
Thank you.
Sure, sure.
So yes, it works perfectly. So this SOK talk is given by Nele Mentens. She is a professor at KU Leuven in Belgium and Leiden University in the Netherlands. You have already met her during our very first tutorial. Her research interests are in hardware security and configurable computing. So Nele, please take it away.
Yeah, thanks a lot. So indeed, this talk will be on network intrusion detection on FPGA related to our systemization of knowledge paper. So I'll try to give a high-level overview of which techniques are used and give a comparison, and also the limitations will be discussed. If you have more in-depth questions, then I refer to our paper, and of course you can ask those questions here. Also, I think that all co-authors are also present at this moment. So what is the motivation for this work? There's an increasing amount of internet traffic through web shops, streaming services, social media, etc., and network bandwidth is also ever increasing. This also comes with an increasing attack surface, so there's more and more attacks, better and better attack capabilities, and all of this requires for up-to-date intrusion detection systems or network intrusion detection systems. And these systems also need to be able to operate at high speeds. So our approach is to focus on network intrusion detection at line speed, which means that we want to process data at the speed that they come in to the intrusion detection system. And the way we do this, or the way we accelerate the network intrusion detection system, is by using FPGAs. because FPGAs are capable of handling much more data in a parallel fashion, and also FPGAs have a much larger I/O bandwidth, so input-output bandwidth, such that they are capable of handling much more traffic in a given amount of time. There's 3 approaches that we looked at. Actually, the last 2 are approaches that we are really working on. That's flow measurement and machine learning, and we also compare to a more traditional approach, which is pattern matching. So what we did was we compared the 3 approaches and looked at which work had been done on FPGA implementations. We looked at the metrics that were, in our opinion, the most important, and we also gave an overview of the limitations and challenges of each approach, and that's what I will present now. So yeah, our contribution to space was, like was already mentioned, with a hands-on tutorial using Python to simulate these approaches, and that was given on Friday. The tutorial is still available online as a Jupyter notebook, so you can still have a look, and I think the recording is also still available, where you can see the link on which you can find our tutorial. And then today I will give an overview of what we did and present our systemization of knowledge paper. So when we look at intrusion detection systems, then the 2 most important categories are network-based intrusion detection systems and host-based intrusion detection systems. So where a host-based IDS resides at a specific host, a network-based IDS monitors the traffic in the network. And we looked at the 3 techniques that are, in our opinion, the most important, and that's pattern matching, flow measurement, and machine learning. So these 3. So I'll give a quite high-level overview of these 3 techniques and also give a few examples of how they are implemented, and then we'll go on to the comparison that we did and discuss the limitations and open challenges. Okay. So first of all, when we want to accelerate this with FPGAs, it's important to use the right boards. And fortunately, FPGA vendors have put a lot of effort in providing new boards in the newest technologies that can deal with very high network speeds. Like this example that you can see here, the Alveo board can handle network traffic up to 200 gigabit per second, which is a lot. But of course, it's not enough to have the interface to deal with this kind of traffic. We also need to make sure that we can process the data that come in. So in our FPGA architectures, we also need to make sure that we, in order to do on-the-fly intrusion detection, that we can process the data at the speed that the data come in. And that is the main challenge. You will see that this is not yet possible for all of the 3 techniques that I just mentioned, but that is our ultimate goal to make this possible. And as you will see, each of these techniques has its own advantages and disadvantages. So depending on the scenario, it might be better to use like one over the other. So when we then look at the 3 techniques that we discuss in our overview paper, the first one is based on pattern matching. And this is probably the easiest to understand. So network packets come in and they are checked on specific fixed rule set. So this is to detect if there are rule violations. And I put fixed here in brackets because these rules are typically fixed over a certain amount of time. And of course, they can be updated after a certain amount of time. And then this has to happen if we implement the rules on the FPGA, then of course this update has to happen when the FPGA is already in the field in the network intrusion detection system. Typically, these rules are based on regular expressions, and you can see an example here. This is an example from the snort rules, which are actually very well known and very popular. And you can see that like there's a lot of things that need to be checked. And if we want to implement these kind of regular expressions on FPGA, then there's several ways to do this. And we can use either deterministic finite automata, or what is actually used much more because of resource efficiency, or non-deterministic finite automata. which can handle a lot more rules than DFAs. So in NFAs, we typically manage to check the regular expressions in a much more parallel fashion than with DFAs. I will not go much further into detail on this technique, but rather focus on the two next techniques because we did more research on it. So the second technique, so just remember that when we use pattern matching, we check for specific fixed rule violations that are known beforehand, that are captured in a certain rule set, and this rule set is then implemented on the FPGA. So the packets come in, and the bits in the packets are actually checked for these rules based on regular expressions. Then, and we can detect multiple types of attacks with this way of working. Second technique is based on flow measurement, and this technique is used for the detection of large flows. So mainly for DDoS detection, where we will check if a certain flow, certain network flow sends more than what it is intended to send or allowed to send. And when we say network flow, then we mean actually all packets that come in with the same flow ID. What is a flow ID? An example of how a flow ID is extracted from a packet is to take the source address, destination address, source port, destination port, and the protocol that is used. So all packets that come in with this same header are categorized as like packets that belong to the same flow. And then the question is this flow sending more than what it is intended to send? Because then we should block it, because then it is more likely to contribute to an attack. So how is this used? When we do flow measurement, then the system typically contains a lookup part and a measurement part. So network flow comes in. There's a parser that then extracts the flow ID, and this flow ID is then used to do a lookup in a blacklist. So in this blacklist, all flow IDs are present that should be blocked. So if the flow ID is present in the blacklist, the packet should be dropped. If the flow ID is not present in the blacklist, it should be passed on to the measurement unit. So that's the second part of the system. And this measurement unit keeps track of how much all the flows that come in are sending, such that we can then detect whether a certain flow exceeds the threshold. And then if a certain flow exceeds the threshold, it should of course be added to the blacklist such that it can be blocked from now on. Now, this first part, the lookup, that's just a lookup in a table. And there's many ways to do that, as we will see in the next slide. And the second part, measurement, we just need to count, actually. So each flow that comes in, we keep track of which volume is being sent through each packet. And then we keep on counting and we keep on adding and comparing to a certain threshold. So you might say this is easy. We just need to do a lookup and we just need to count the volume of each flow that is being sent. And this is easy, actually. And this is especially easy if we can do it at a very slow pace, if speed is not important. But when speed is important and we need to take care of a lot of data, then this becomes challenging. And especially what I mentioned before, like when we have network bandwidths of like 200 gigabit per second, then this is not straightforward to do. So when we look at these two most important parts then of a flow measurement architectures, then first we have the lookup. So one way to perform a lookup is to use a content addressable memory. This is an exact data structure with no false positives or negatives. So we ask the CAM to check if a certain flow ID is present in the blacklist, and the CAM will tell us if it's there or not. The disadvantage is that this takes a lot of resources, typically relatively high power consumption, and also when the content addressable memory becomes large, the operating speed will be very slow. So actually, when we have high bandwidth networks, this is not a feasible option to use in our intrusion detection system. So then what are alternatives? And these are like this, I'm just naming one alternative here, but there are more because I will give the example of this alternative. And that's also something that can be easily implemented on an FPGA, as we also did. And there's actually many variants of this type of data structure. And that's a Bloom filter. So Bloom filters have the disadvantage that they can also have false positives. So these are not exact data structures, but the advantage is that they can operate at a much higher operating speed than a CAM, and they also consume a lot less area, and they have a lot lower power consumption. So the question is, can we accept these false positives? If yes, and if we only have like a very, very low rate of false positives, then Bloom filters are a viable option. And what do I mean with false positives? Of course, when a network flow comes in, it is detected as, it is dropped because it's supposed to be in the blacklist while it's actually not. So what does a Bloom filter look like? So with a Bloom filter, we can do this lookup. So we're talking about the lookup architecture. So this is an example of a very small Bloom filter. So it is a one-dimensional data structure. It's a memory array with 1-bit cells. So in the beginning, all the cells are reset to 0 when there is no data in the memory structure or in the Bloom filter. We use k different hash functions to write something to the Bloom filter and to also query a certain value from the Bloom filter. So I'll give an example where k is 2. If we want to add a flow with flow ID equal to x1 to this data structure, so a certain flow comes in, the parser extracts the flow ID, like I said before, this combination of source and destination address and ports and protocol. Then this value is used and is hashed actually with k different hash functions, where k is 2 in this example. So in this example, x1 is the flow ID. It is hashed with h1 and also hashed with h2. And then this h1 and h2 are used as addresses in this one-dimensional data structure. And at those addresses that h1 and h2 point at, a 1 is written in the memory structure. Then we can add a second flow ID comes in and is added to the data structure. So this is actually to fill the lookup table. And in this case, it's x2. So we use the same two hash functions, h1 and h2, and we write ones at those address locations. Then x3 comes in, and it might be that x3 points to one memory location where x2 already put a 1. Then we leave this 1 there, and x3 also points to a new memory location. So this is to fill, to add values actually to the Bloom filter. And as you can see, you can already guess where the fact that we don't have 100% accuracy, where that comes from is, of course, that certain hash values can point, so certain hash values belonging to different flow IDs can point to the same memory location. And then when we query, for example, we want to check if x1 is present in the lookup structure or the data structure, then we take the flow ID x1 and we perform the two hash functions, h1 and h2. We go to this memory address and we check if there is a 1 present or not. In this case, we see that there's a 1 at location h1 and also at location h2. So we know that x1 is present in the data structure. If we want to check for x4, and it turns out that it's not the case that both memory locations have a 1, then we can say, okay, x4 is not present in the data structure. If we then search for x5, which is actually not present in the data structure, but still we see 2 1s at those 2 locations, then we have a false positive. So this is how a Bloom filter can use a lot less memory than a CAM memory, but can have false positives when we do the lookup. So we have a lot of reduction in terms of resources and high increase in speed, because in this case, like performing these hash functions, if we can use fast hash functions in hardware, then this can be a very fast process. So that was to give you an idea of what kind of lookup structures are there and which ones are actually efficient in hardware. Then if we look at the measurement part, so we already did lookup. Now for those packets that are not in the blacklist, we need to count for which volume is being sent by this specific flow ID or by a specific flow. Then we can use associative counter arrays, which are actually also which are 100% accurate, but also have a high memory overhead because they do exact counting and a low operating speed when we need a lot of counters and when we need large counters. So the benefits and disadvantages are a bit comparable to CAM memories when we were talking about lookups. As opposed to associative counter arrays, we can also have probabilistic counting architectures, just like we had Bloom filters for the lookup. These are also data structures or counting architectures with a certain probability of error, but they operate at a much higher operating speed and they have a lower memory overhead compared to associative counter arrays. So I'll also give one example of these. One example is CM sketch. So CM sketch is a 2D memory array of counters that is again indexed by K hash functions. So what happens if we want to add, so we are not doing a lookup now, but we are counting. So a certain flow comes in with a certain flow ID, and we need to keep track of the volume that is being sent by this flow. Doing that, we can look at the exact volume in each packet and then do plus volume here in each counter. But in this example, we just do +1 whenever a certain flow ID comes in. So this could be plus n in principle. So when a certain flow ID comes in, we again use two hash functions in this example in order to point to specific counters. And we do +1 for those counters that we are pointing at. We can do the same for another flow ID and for another flow, and we can, and it could be that again, the flow ID which corresponds to X1 comes in again. So we need to add +1 again. And this way we can keep on counting how much of a certain flow comes in, or what the volume of a certain flow is. If we then want to add another flow, X3, then it could be, of course, that X3 points to a memory location or a counter location where we already had another flow that was present, in this case, X2. So then that means that this specific counter now represents part of the value from X2 and part of the value from X3. So if we now want to query, we want to see how large is the flow ID that is equal to X1, what is the volume sent by this flow. Then we look at the memory locations or the counter locations that this flow points at after using the two hash functions. And then we take the minimum of those two locations. And in this case, we can say that the volume sent by X1 is 2. If we then check X2, this is why we take the minimum. You can see that in one counter location we have 1, and in the other one we have 2, because X3 also contributes to this location. And then we can say the volume is 1. Of course, if we have now a certain flow where the two hash functions point to counter locations that are only filled by other flows, then we get an overestimation here. And that is the error that I was talking about. Of course, we can also clearly make trade-offs between how large the memory should be and how small the estimation error should be. So this is a trade-off that we need to take in hardware. So that was to give you an idea of, when I go back, to give you an idea of these two important parts that we have in flow measurement and where we can have efficient structures on FPGA, of course, with a certain probability of error. Then when we look at the third technique, machine learning, then this technique has the advantage that we can not only detect known attacks, like in the first technique, pattern matching, we were searching or we were comparing to a certain rule set and checking if certain rules were violated by doing pattern matching and by checking what the packets actually look like that come in. With machine learning, we can also detect known attacks if we train the network for these known attacks, but we can also detect if there are deviations from normal traffic. And this is a big advantage compared to the other two attacks, to the other two techniques. When you look at research on intrusion detection systems using machine learning, then there's a large variety of data sets, feature selection methods and algorithms. And in order to make a fair comparison, it's good to use commonly used data sets like the ones mentioned here on the slide. Although some of these are also outdated or consist of simulated traffic, but yeah, of course, when you write a research paper, you also need to compare. And reviewers don't like it if you don't compare. So we need to use all these data sets that are being used for years already. At least we try to use the most recent ones and the one that we find valuable as well in our research. Then there's also different types of algorithms that are used, which are listed here. And more recently, also deep learning algorithms have been used for network intrusion detection. That doesn't mean that all these algorithms are already suitable for being implemented on an FPGA, at least not when we look at the more complicated architectures. So actually, we made an overview of all the work that has been done on FPGA. Actually, this was the part that Laurens took care of. So he made a nice overview of which types of algorithms have been used on FPGA, which data sets were used. And as you can see, the main metrics that are used here is like how many resources are used on an FPGA. And then that basically tells us, if we can fit the algorithm on the FPGA or not, depending on which FPGA we choose. Latency is also an important metric. And if we look at network intrusion detection, like I said from the beginning, the throughput or the bandwidth is very important. And in the beginning, I mentioned that we want to go in the direction of like 200 gigabit per second bandwidth. As you can see, we are still further away from this, although you can see here some results that appear to be surpassing this bandwidth. These are mainly on very limited architectures, actually, that are probably not viable yet for real world applications. And you can also see the accuracy here then, which is also important, of course. Now, if we compare all the properties of these network intrusion detection systems, this is important for like when you want to start using such a system, and when an FPGA is also used to make sure that we can accelerate the NIDS. Then what is important? First, it's the detection capabilities, so the coverage. Which types of attacks can be dealt with the specific system that we are using. When we look at the flow measurement, then it's mainly like detecting if a certain flow is sending traffic above a certain threshold. So this is mainly to detect DDoS attacks, for example. So it's quite limited to these types of attacks. When we use pattern matching, then we compare against the fixed set of rules. So the rule set is fixed, although we can update it, which gives us already more capabilities than flow measurement, because we can also detect different types of attacks, not only DDoS attacks. And when we use machine learning, this gives us the extra capability of also detecting unknown attacks, because we can also detect when traffic deviates from normal or benign traffic. Then when we look at accuracy, when we use pattern matching, then these are exact matches that we do. When we use flow measurement, like I said, we also use probabilistic structures like these lookup and counting architectures. They are not 100% accurate, but close to 100% if we use enough resources. And then machine learning is probably the least accurate and also the least explainable. Then when we look at expert knowledge, the ease of maintenance, like if you want to install such a system, when you use a machine learning based approach, then you don't need to know much about the system. As long as you have it, you can install it, and everything is done automatically, more or less. For flow measurement, you need a little bit of expert knowledge because you need to set the threshold above which flow is not intended to send traffic volume. For pattern matching, even more expert knowledge is needed because the rule set needs to be determined in every specific case, like which rules cannot be violated. So that's even more difficult. When we look at ease of design, and then I'm talking about FPGA implementation, for pattern matching, these are quite common structures where there has been research for many years already on how to implement these regular expressions on FPGA. So if you look at the literature, that's relatively easy, I would say. On the other side of the spectrum, we have machine learning architectures where there's still a lot of ongoing research on how to make these architectures faster and faster on FPGA, and flow measurement architectures are somewhere in between, I would say. Then when we look at detection speed, with pattern matching, we can easily get above the 200 gigabit per second that I mentioned as an example. With machine learning, we are not there yet if we want architectures that have that cover or that are sufficiently complicated to cover a number of attacks with a high accuracy. And flow measurement is somewhere in between. There we can get to hundreds of between 100 and 200 gigabit per second already, if we have FPGAs with enough resources. And like I said, hardware efficiency then. So with machine learning, it's mainly the fact that it's very difficult to put a decent neural network on an FPGA with sufficiently high speed. So this is the largest challenge, I would say. And then the pattern matching techniques are the most efficient in hardware. And that also comes with a high detection speed then. And for flow measurement, they are somewhere in between. If we look at the challenges that are still open, one challenge is how to deal with encrypted traffic, because now, we assume that, especially for the pattern matching techniques, that we can look at the whole payload. Also, for machine learning techniques, it depends. Sometimes only the header is used, sometimes part of the payload is used. For flow measurement, it is mainly the header that is used, but there are also some internet architectures where even the header is encrypted. So we need to have a look at how to deal with this. Then one important thing is also that the FPGA needs to be large enough, because if you need to go off chip, for example, for some machine learning architectures, we need external memory. And this, of course, decreases the speed a lot of the whole architecture because of the communication overhead between the external memory and the FPGA. And then also, in some cases, we need to do fast updates. For example, if you want to update the rule set in a pattern matching system, then the system cannot be offline for too long. So the updates have to happen fast. So the question is how to do that in a sufficiently fast way. So in conclusion, we compared different approaches to network intrusion detection on FPGA, should be pattern matching, flow measurement, and machine learning. We made a comparison based on detection capabilities, expert knowledge required, detection speed, and resource efficiency. And as I showed on the previous slide, several open challenges remain. So at least I think it's an exciting research topic. Thanks.
Totally. Thanks, Nele. This is fantastic. So questions from the audience.
Hello, Neil. This is Bodhisattva. Can you hear me? Hi.
Yes, I can hear you.
So actually, as far as I know, maybe it would be a naive question. Basically, what I have learned is that that basically the ternary content addressable memory-based TCAM-based designs are the most visible designs on FPGA platform when we consider this in a network intrusion detection systems. So are there any other systems other than TCAM-based designs which are ported on FPGA platforms?
So if you want to make use of TCAMs, then indeed you have, maybe that's what you mean, like the tools already have support for that. So for somebody that doesn't want to take the time to design the data structure or lookup architecture.
Yeah, basically TCAMs have the problem of they consuming a lot of resources. So
Indeed.
Though they deliver the maximum throughput, but they consume the largest resources. So so other than TCAM, is there any other designs that are available on FPGAs?
Yeah, supported by the tools directly, not. But of course, when we make our own implementations, then you have these structures like the one I gave an example for, like the Bloom filter structure, for example. But that's then an own design, of course. I don't know if that's what you were pointing at, or if you mean like what is provided by FPGA vendors, because if we look at what is provided by FPGA vendors, then I think it's only the CAM structures, and then indeed they take a lot of resources, and depending on the application, it's okay or not. Depending on it's
okay. I got it. I got it.
Sure. Thanks a lot.
Thank you.
We have time for another 1 or 2 questions. So. Okay, so I actually have one question before I'll just take that one question time then. I really liked the whole systemization of this flow measurement and then pattern matching and ML and the matrix that you ultimately came up with. That was a really eye-opening this table. But I was wondering is that, so is it that the network intrusion detection was viewed as a single type of attack, or are you actually considering different attackers who wanted to like intrude in a network, like, for different purposes, like for example, like for different attacks? So I was just wondering whether you consider the dimension.
Yeah, so I think what you mean is related to the coverage that we have in our table. Please correct me if I'm wrong. So
yes.
What we meant with coverage is like the breadth of attacks that are covered by the different systems. And clearly when you look at flow measurement systems, then it's all about like the volume of the flow or sometimes the frequency of some flow. So that's quite limited to that, although that's an important type of attack. And then with pattern matching, you can fix any rule actually in your rule set, so you can cover a lot more. And with machine learning, you can also detect everything that deviates from normal benign behavior. So probably there you can even detect attacks that you didn't know of before. I don't know if that answers your question or
that does. And then the follow-up question is is it true that pattern matching is the best? Most of the times it is actually better than others, like aside from machine learning on coverage and ease of maintenance angle, it actually looks like pattern matching is trumping all else, which is a bit surprising. So
maybe I don't know which other metric we should have added to also show that it's not something that we can use in any situation, of course.
Right.
Because indeed you need to have this. Maybe this one is the most important, this ease of maintenance, then to show that it's not perfect for all scenarios, of course, because you need to have this rule set fixed beforehand. And if you don't define the rule set properly, then it's not worth anything actually. So that's actually also a big disadvantage then. So if you look at it like that, now it looks like it's really much better than the rest. But maybe we should have put in like weights to the different metrics. And I think it depends on the situation, also on the application.
So I was wondering more like adaptability, perhaps like ease of maintenance, so more like adaptability to new attacks kind of thing. So
that's true. I think that's maybe like versatility or something. I see what you mean.
Okay.
Thanks a lot.
Thank you. So let's thank the speaker, and that will conclude our last paper session for space. So please hold on though. We have one very last